This is the second video in a sequence on the optical properties of solids. And in particular, this is going to be about definitions and terminology, because there's a lot of confusion about what the words mean, and also that we have a tendency to use the letter K too much, which I'll get into. So let's start with reflectivity and transmittance. Unsurprisingly, reflectivity has to do with reflections. Here I have some light that is coming into a slab of material. It has a flux F incident, F inc. That is the incident flux. When it hits the material, some of it will be reflected, and that reflected portion has a flux of F refl. The reflectivity, capital R, is the ratio of the reflected flux to the incident flux. Similarly, transmissivity has to do with the amount of light that is transmitted through, that makes it all the way through the material. So now I've had my instant light hit here. Some of it has gone into the material, it's propagated through and come out the other side. And when we measure the light that comes out the other side of our material, we find it has a flux, a transmitted flux, F trans. Our transmissivity, T, is F trans, transmitted flux, divided by F inc, the incident flux. Now, both of these quantities are going to be wavelength dependent. Remember that if I was wearing a red t-shirt, then it would be strongly reflecting red light and not reflecting the non-red light. If there is no absorption, so if the light passes through this material without being absorbed at all, then the reflectivity and the transmissivity should add up to 1. Think of this as being, they're both adding up to the instant radiation. Both the reflectivity and the transmissivity are measurable. That is, we can put a detector here and measure our reflected flux, and we can put a detector over here and measure our transmitted flux, and we can measure how much light we put in the first place. Now, in a real medium, you're going to have a couple of effects that happen in transit through the material. You're going to have refraction and absorption. So we can't just say that the transmittance or transmissivity is just 1 minus the reflectivity, because now some of the light gets lost along the way in its passage through the material. So here's my slab of material again. Here's my incident light and my reflected light. Here's the light that's being propagated. Some of it may be reflected at the surface, and then some of it is transmitted through. What we can say is we've got the instant light and some of it is reflected. And if the reflection at this point is R1, then the amount of light that makes it into the slab is 1 minus R1. That is then affected by some sort of absorption. That's what this term here is for. We're going to come back to this in some more detail later. That will then be reflected again at this surface. So now if we have a reflection here, R2, then the amount of light that actually makes it out is given by this equation here, where we have the transmitted light is, we take away the reflected light, we take away some that's absorbed in the middle, and then we take away the second reflection, and what's left gives us our transmitted light. We can probably assume that we're going to get similar reflections at this interface and this interface, and so we can make R1 and R2 identical, and then we get an equation like this. And so now we've got something where we can say we can measure the reflected light, we can measure the transmitted light, and we can measure the thickness, L, of our slab, and that means that we can extract the absorption properties of this material. So what's going on when light is being absorbed by a solid? You can think of this as being, there is a loss of energy from the radiation and a gain of energy to the atoms or molecules in the material. So the light is being lost to the material, and that means that the energy in the material is going up. Now, the energy of an assembly of atoms is a mixture of the thermal energy, that is how much it's moving, and the internal energy, where the internal energy is actually nuclear. It's basically a mixture of the energy associated with binding the electrons to the nucleus and the binding of the nucleus itself. But that has nothing to do with the energy that it's going to absorb. Much. Okay, so let's keep going with these physical processes. If you've got an atom, then you only have electrons that can move and absorb light. But if you've got molecules, they can have some other oscillations. We can have some wiggling of bonds and some rotation. And when we have a solid, we now have not just the bonds between atoms in a molecule, but we also have the bonds between molecules that make it solid. And so when we have radiation that's being absorbed, it can be absorbed as an electronic transition, it can be absorbed as a molecular bond wiggling, and it can be absorbed as an intermolecular bond. And for that reason, solids are very good at storing energy in a way that atoms and molecules aren't. So here what we can see is that for systems at the same temperature, if we just have a monoatomic gas, the only thing it has is its kinetic energy. If you've got molecules, now you've got some vibrations between the atoms that are stuck together, they're bonded together in the molecules, and also the rotation of those molecules. But if you've got a solid, now you've got this internal energy that is the intermolecular bonds that are able to wiggle and store energy. And so you can store a lot of energy in a solid. And this is actually one of the reasons that dust is so impactful in the environments that we find it in, especially in space, because it has such a big impact on energy flow. Video is on various definitions. Let's get into refractive index and absorption. If we have a transparent medium, or usually the way you learn refractive index when you're in middle school, is that it is simply the ratio of the speed of light in vacuum to the speed of light in the medium. Here it's written as N, and that's the speed of light C and the speed of light in the medium V. This is going to be wavelength dependent. I think you all have come across this in terms of prisms, that the refractive index changes with the color of the light. Now, absorption is another property. So here I've got this as transparent, but it could be also absorbing some light along the way. That is quantified by the concept of absorptivity. So just like we had transmissivity and reflectivity, we also have absorptivity. And it has a very similar definition. The absorptivity is the ratio of the absorbed flux to the incident flux. Now, the incident flux is what we give it. We cannot measure absorbed flux directly. We can measure reflected flux and transmitted flux and get the absorbed flux out, but we cannot measure it directly. But we can also define a term that is called the absorption coefficient. And here I've called it kappa abs. You'll see in different textbooks, it might be K abs or kappa abs, or sometimes alpha abs. Different letters get used because, well, we'll see in a minute. This absorption coefficient here is essentially the fraction of light absorbed per unit length of the medium. So you can think of it as being, it's related to the absorptivity because it's the F abs over F inc, but now it's got a component that relates to how thick the slab is. So let's just go off at a tangent for a second and talk about the letter K. Now, I just mentioned that the absorption coefficient is sometimes kappa, it's sometimes K. K is a problem because we use it for too many letters. It can be used for mass absorption coefficient or opacity, and we'll come to those definitions in a little while. K is used for the wave number, the imaginary part of the complex refractive index, which we'll come back to. So remember, wave number is related to frequency, or 1 over the wavelength. The imaginary part of the complex refractive index we haven't got to yet, but we will talk through that in another video. We also have the Boltzmann constant, which is used in many different thermodynamic situations, and that sometimes has a subscript B, but usually it's just K. Sometimes opacity is called K, sometimes the mass absorption coefficient is called K. It gets very confusing when there are all these different ways that the letter K gets used, and we need to distinguish between them. So I'm just warning you, it will get confusing and different people will use different letters for the same thing. So let's define opacity. Opacity, the word, comes from the idea of being opaque. Opacity is opaqueness. Basically, it's how opaque is a thing. And so we're going to define it here, but here what I've got is a slab of material. I've got light of incident flux F, and after it has passed through this slab, which has a density rho and a thickness dx, it has a value F prime. So the light is passed through, something has happened to the light along the way. It has propagated through. It may have been absorbed. It may have been scattered. And now we see light that's come through the other side. And what we can say is there is a change in the light that is simply the difference between what we started with and what we ended with. But that difference in light depends on the opacity or mass absorption coefficient. That's this K sub lambda. Remember, all of these values are wavelength dependent, and so there tends to be a little sub lambda there. So this is the opacity. The density, because you may have a material that has an intrinsic opacity, but if you make it denser, it will be more opaque. Then you have the amount of flux that hit it in the first place, and you have the thickness. So as it goes through, more light will be absorbed if the thickness gets thicker. If the density gets higher, then more light will be absorbed. So this gives us a definition for what opacity is. And it's basically to do with how light is removed, and it depends on the material and the wavelength. So now I've just rearranged this equation so that all my F lambdas are on one side, and I've integrated. And so what I've got is that as the light goes into the slab, as we go in a distance x, the light is going down exponentially. So as we penetrate the slab, the amount of light goes down from the 0 value, which is this edge, exponentially, and it depends on the opacity, the density, and the thickness. I want to introduce the idea of optical depth. So optical depth is basically where you take this whole term here, the K, rho, and X, and that all put together is the optical depth. Although it's called depth, it is not a distance. It is unitless. It is dimensionless because it's just the power, okay? But it is an overall measure of how much light is removed. So you can think of it as being, if you're looking at a slab of material or a cloud that you're looking at, and you're seeing that light is removed, and you don't know what it's made of or how dense it is or how thick it is, you just know a bunch of light was removed, then the optical depth is basically saying, this is how much light was removed. This kappa abs here, the absorption coefficient, is just what you get when you multiply the opacity by the density. So this is that diminishing of the light with distance. So you still need the distance through to get the actual amount of light diminished. Again, this is sometimes called the absorption coefficient. And this is what's known as Beer's law. Now, in this case, this assumes there's no reflection. Remember, in our previous slides, we had reflection at this surface and reflection at this surface. In this case, we're assuming that our reflections are negligible, so it's just what passes through that matters. So let's just revisit that coefficient confusion again, because there are lots of different coefficients, and that absorption coefficient, that is the kappa abs, sometimes called the volume absorption coefficient, is also sometimes given the letter alpha. We also have a thing called absorbance, which is not the same as absorptivity, and it's sometimes also alpha, and it's basically the equivalent of optical depth. So it is that power that is defining how much light is lost. We also have this letter K that we use for opacity, but it's also used for the imaginary part of the complex refractive index. Again, we'll get into this in more detail later. And that is also sometimes called the absorption coefficient. And then we have the mass absorption coefficient, and that is the opacity. And so kappa, the volume absorption coefficient over the volume. So this has got a mass component in the units. So it has to do with how much material you have in terms of mass. Confused yet? The point of this is that it can be very unnerving to not know what all the letters mean, and it's useful to keep good notes and figure out your own way of making the terminology work. Sometimes we use extinction or attenuation instead of absorption, because that then encompasses light that is removed and not necessarily by absorption. It could be by light scattering, so back reflections. What we've got is something that is more general in terms of attenuation or extinction, but it's often used interchangeably. Definitely designed to give you a headache. So let's get back to refraction and absorption. So remember, we talked about this one before. We've got a real medium. We've got our light passing into our material. It's propagating through and it's coming out the other side. that we're going to have a reflection at each surface. And so we end up with a term that gives us the transmission, the reflection, but now we understand what this kappa is. So now I'm going to say these two reflections have the same magnitude. So we've got a reflectivity, a transmissivity, and now we've got this e to the kappa L, where L is the thickness of the slab and kappa is now our absorption coefficient. And so now, because we can measure T, R, and L, we can extract kappa, which also means we get the opacity. And that's a major way that we can actually determine what the optical properties of solids are. Again, revisiting some of the terminology. So we've got reflectivity and absorptivity. Now, it is also called transmissivity, but it's usually called transmittance. But reflectance and absorbance are not the same as absorptivity and reflectivity, even though transmittance is the same as transmissivity. So here I've got reflectivity, which is the fraction of reflected light to incident light, the transmissivity, which is the fraction of transmitted light compared to incident light, and the absorptivity was the fraction of absorbed light to incident light. But the absorbance is that power, the same as the optical depth. So now this is the kappa L or the K rho L. So this is how much light is lost in a given material. And so it depends on the intrinsic absorption property, the opacity, the density of the material, and the thickness of the slab. And it's related to absorptivity by this equation. The transmissivity or transmittance is related to the reflectivity and the absorbance, or the reflectivity and the absorptivity. And so we can see how they all fit together. But we do want to be careful with this terminology because absorbance and absorptivity have very distinct meanings, as do reflectance and reflectivity. So let's introduce the idea of the complex refractive index. I mentioned this earlier, but I want to bring it up again and get into it in a little more detail. Normally, when we think of the index of refraction, it's simply that ratio of the speed of light in vacuum to the speed of light in a medium. But now we're going to include a second component. So now it is a complex number where we have a complex refractive index with a real part, which is the part you normally think of, and an imaginary part. What we get is that this part here, this K, this imaginary part of the complex refractive index, is sometimes also called the absorption coefficient and sometimes the extinction coefficient. And it's not the same as the other extinction coefficient. Again, I will tend to refer to it as the imaginary part of the complex refractive index. It's wordy, it's cumbersome, but at least it is unambiguous. Just to remind you, this K is not the same as kappa abs or the opacity, that K sub lambda, but this is wavelength dependent. Now, there are two sets of optical constants. And when I say constants, that's a term that seems to have become embedded in the literature. They're not really constants. These are functions. This is wavelength dependent. But there are two of them, and they are closely related. We have the real and imaginary parts of the complex refractive index and the real and imaginary parts of the complex dielectric function, which is basically the relative permittivity. So we'll be getting into this in a future video. And these two are interrelated, and that's going to be important for us to understand how the electric field of the light affects materials and how that manifests itself as the complex refractive index. So here I have my two sets of optical constants. From Maxwell's equations, we can get that the speed of light is just 1 over the square root of the magnetic permeability times the electric permittivity, and those are the values for free space. And then likewise, the speed in a vacuum is using the relative permittivity. So I've got the relative permittivity and relative permeability of a material. And since we define the refractive index as the ratio of the speed of light in vacuum to the speed of light in a material, then we can basically rearrange this equation so that we get that the refractive index is related to the permittivity, the relative permittivity of the material, and the permeability of the material. In general, the permeability is not going to have a big effect, and so we can usually ignore it. It's typically 1. There are going to be cases where that's not true, but in general, we can ignore it. And so what we have is that the complex refractive index is related to the complex dielectric function by this relation, square root. Just to summarize this introduction to some of these ideas that we're going to need to use to understand the optical properties of solids, we went through some definitions and terminology. We talked a little bit about the physical processes of absorption, that is, that it is energy from light that is then trapped by a material and it's absorbed in different ways. We talked about the letter K and how complicated things get when people use the letter K all the time. We talked about opacity and optical depth, absorbance versus absorptivity, reflectance and reflectivity, and that transmittance and transmissivity are the same thing. I'm pretty sure that we actually use transmittance because transmissivity is hard to say. And then we introduced the complex refractive index and related it to dielectric functions and Maxwell's equations. And that's it for this video. We will be back with the next step in understanding the optical properties of solids in the next video.